So far, most of the theory and algorithms that we've explored so far have looked at differentiable functions or functions that are smooth. But this is not always the case in a lot of interesting applications. So we've actually already seen some non-smooth convex functions that arise quite naturally in common applications. So things like the hinge loss, which is the max of some linear function in zero, or the L1 norm. And just visually, we see immediately that these are not differentiable everywhere. And it turns out that the fact that there are points where the derivative doesn't exist is going to be a problem because very often these points actually end up mattering when we're trying to solve this problem. So today I want to talk about some common approaches for non-smooth optimization. And the key idea when minimizing non-smooth functions is the subgradient. So if we look back at our analysis of convex functions and convex optimization, what we'll see is that very often the way in which the gradient actually comes up is in the context of this inequality that f of y is greater than or equal to f of x plus the gradient of f evaluated at x transpose times y minus x. And the fact that this inequality holds for all y and x in Rn is what really underlies a lot of the theory and algorithms for convex optimization. And it turns out that if f is not differentiable at a particular point x, we can more or less just reproduce all of this theory by using what we call a subgradient, which is just any vector g that satisfies this kind of inequality for all y in Rn. Now, one of the things that's really different than when we're dealing with smooth functions is that there can be more than one subgradient of a non-smooth function at a particular point. And so rather than talking about the subgradient, we talk about what we call the subdifferential, which we give the notation delta f of x. And this is just the set of all possible subgradients of f at x. Now, if f is convex and differentiable, then the subdifferential is just one vector, which is given by the gradient. However, for f that are not differentiable, the subgradient may contain many vectors. And for non-convex f, the gradient might not necessarily be a subgradient. And there can also be points where neither the gradient or subgradient even exist. But since we're only going to be concerned with convex problems for now, we're not going to worry about that too much. All right, so let's look at one concrete example of this. So let's consider the L1 norm. So f of x is just the L1 norm of x, and we want to look at the subdifferential of this function. So the L1 norm is not differentiable at any x that has at least one coordinate equal to 0. We'll see that optimization problems involving the L1 norm very often have solutions that are sparse, meaning that they have many 0 entries. And so this is really a significant problem, right? So the non-smoothness is kicking in exactly at the points that we're going to be interested in. So what does the subdifferential look like in this case? So recall that by definition, if a vector u is in the subdifferential of the L1 norm at the point x, then what we must have is an inequality that looks like the L1 norm of y is greater than or equal to the L1 norm of x plus u transpose y minus x. We can understand this a little bit better by defining some special notation here. So let's let gamma of x be the set of indices n where xn is not equal to 0. With this notation, we can look at the right-hand side of this inequality and rewrite it. So first, just note that the L1 norm is just the sum of the absolute values of the entries, and this inner product is just going to be the sum over all entries of un times yn minus xn. And note that if xn is equal to 0 outside of gamma of x, then xn isn't contributing anything when n is not inside of gamma. So we can actually combine all the terms involving xn and just write that sum over gamma. And then we have this remaining term, which is just the inner product between yn and un. So what we'd like to do is understand how can we choose u to make this inequality hold? For what u will this right-hand side actually be less than the L1 norm of y? Well, suppose that un is constructed as follows, so that un is equal to the sine of xn when n is in gamma. So it's either plus or minus 1, depending on whether or not xn is positive or negative. And whenever n is not in gamma, so when xn is equal to 0, we can just take un to be anything with magnitude less than or equal to 1. Now, if we take this construction of u, then let's look at the first term. Whenever xn is positive, un is going to be equal to 1, and whenever xn is negative, un is equal to negative 1. And so in that case, un times xn is just the absolute value of xn, and this entire sum will just be 0. Now, what can we say about this second inner product? Well, if the magnitude of un is always less than or equal to 1, then what we can say is that un times yn is always less than the absolute value of yn. And so this sum is going to be at most the L1 norm of y. And so what we've just done is shown that if u is constructed in this way, then it does satisfy this inequality and it is a subgradient. And it's not too hard to show that in fact all subgradients have to satisfy this inequality. In the homework, you'll see some examples of other subdifferentials, but this is a really important example. We'll encounter this again. Okay, so now that we've introduced this notion of a subgradient, what can we do with this? Well, for one thing, we can derive a new and improved version of the optimality conditions we talked about for convex optimization that now allow for non-smooth objective functions. So in particular, if f of x is convex, then it's easy to show that x star is a solution to the minimization problem where we would like to minimize f of x over all x in Rn, if and only if the 0 vector is in the subdifferential of f at x star. So before we wanted to say that the gradient of f was equal to 0. Now it's possible that f might have many subgradients, and all that matters is that one of those subgradients is 0. And this is easy to show. So first of all, let's show that if 0 is in the subdifferential, then we have a minimum. Well, if 0 is in the subdifferential, then what that means is that 0 is a subgradient, so it satisfies the inequality f of y is greater than or equal to f of x star plus 0 transpose y minus x star, but that's just 0. So what we've just shown is that f of y is greater than or equal to f of x star for all y, so x star has to be a minimizer. Similarly, if we suppose that x star is a minimizer, then that means f of y is greater than or equal to f of x star for all y, and so trivially we have that f of y is greater than or equal to f of x star plus 0 transpose y minus x. So 0 must be a subgradient at x star. So in the same way that this notion of a subgradient allows us to generalize our thoughts about optimality conditions, we can also generalize algorithms we've seen before. So the simplest one will be just a subgradient descent method. This is going to look exactly the same. So the basic idea is that we'll start with an initial guess and then we will update our estimate using the same kind of update rule. So xk plus 1 is just going to be xk plus alpha k times dk, where before d was the negative gradient and now d is just going to be the negative version of any subgradient at xk. Just to see an example of this, let's consider a simple example. So the absolute value of x, and suppose we take some initial guess. Well, as long as we're not at the minimum already, we're going to get a vector that points towards the minimum. But what are we going to do once we get to the minimum? Well, this actually reveals one of the big challenges with subgradient descent, because at the origin here, at this minimizer, there are many different subgradients. So one of them is 0, but we see the subgradient inequality is satisfied for many different values. So any slope that's less than or equal to 1 will give us a lower bound here. So this raises a bit of a challenge, because what you're going to see, and this happens in practice, is that if we're just picking any subgradient, we might pick a bad one. We might even be at the solution to the problem and pick a subgradient that moves us away from the solution. So as you might expect, our guarantees are going to be a little bit weaker in this case. So what can we show? Well, first of all, since we no longer can guarantee that we're always even going to be making progress at every step, what we'll actually do is keep track of what's the best solution we've had so far, and we'll denote the objective function value at that best solution that we've seen so far by f best k. So this is the best solution up to the kth iteration. And what we'd like to know is, well, can we guarantee that f best k actually will converge to f star, which is the objective function evaluated at the minimizer x star? Well, it depends on what we assume. So to analyze this, we're going to assume that f is Lipschitz, meaning that the amount that f of x can differ from f of y is controlled by some constant times the L2 norm of the difference between x and y. So first, if we use a fixed step size alpha, then using an analytical approach is very similar to what we used when we were analyzing gradient descent before. What we can show is that f best k minus f star can be bounded by a term involving the L2 norm squared of x naught minus x star divided by k, plus an additional term that depends on this constant g and the step size alpha. And so note that no matter how large k grows, this second term will always be here. And so with a fixed step size, we can't guarantee convergence to the true minimizer. But what we can do is consider a decreasing step size. So it turns out that to get optimal results in theory, you would choose something like alpha k being proportional to 1 over the square root of k. And in this case, we get a convergence guarantee that looks more like the initial error divided by square root of k plus some constants times log of k over square root of k. And so now, as k gets very large, both of these terms do go to 0. So if we set this whole thing to epsilon, then what this is telling us is that to get convergence to within epsilon, we need k on the order of 1 over epsilon squared iterations. Unfortunately, this is pretty slow. And sadly, this is really the best kind of guarantee that we can get for subgradient descent. In the notes, we look at an example of a particular optimization problem where we're doing subgradient descent, and we look at the performance. And what you'll find is that fixed step sizes really do behave quite poorly, and you do get improvements by having a decreasing step size. In practice, you might want to be more aggressive at how quickly it decreases, but there's really no hard and fast rule that's going to do better than what I'm showing right here. So the subgradient algorithm is one generalization of gradient descent, and it's simple, but the convergence is typically very slow. And the reason for this is that there are plenty of subgradients that are large, near, and even at the solution. One way to deal with this is to think about adding some kind of smooth regularization term. So suppose we take our minimization problem, and to the objective function we add delta times the L2 norm squared of x minus x star. Note that this quadratic term is going to be equal to 0 at the solution, and for any x that's not equal to x star, it's going to be strictly positive. And so adding this regularizer doesn't actually change the solution to this optimization problem. However, once we add this, now it turns out that this is strictly convex, and the only subgradient at the solution will be equal to 0. So this addresses a lot of the drawbacks of subgradient methods. But of course, this is not really an actionable algorithm because it is using the solution x star to form this regularizer. In general, the whole point of this is that we don't know x star. So how can we use this idea? Well, what we can do is adopt an iterative approach, so the proximal point method. So what this method does is say we have some xk, and we'll use our current guess xk to form this regularization term. And we will solve this problem, and that will give us xk plus 1. And then we'll repeat this process using the new guess xk plus 1 to form the new regularizer. We call this mapping that takes xk to produce xk plus 1 by solving this optimization problem, the prox operator. So prox alpha f of z is just going to be the solution to this optimization problem when z controls our regularizer. And so we can then use this notation to very concisely write xk plus 1 is just prox alpha kf of xk. Okay, so before I go any further, I think I have to address what's probably on your mind, which is what are we actually doing here? Because we have taken an unconstrained optimization problem that was hard to solve, and now we've turned it into a sequence where we're going to have to solve an optimization problem at every iteration of this algorithm. So how is this helping us? Well, when you're going to use this method, you're going to want to use it on cases where this prox operator is actually relatively easier to solve for some reason. One way to think about this is just that adding this regularizer makes these problems much better conditioned. And so algorithms for solving this problem will converge very quickly. And so it's okay to solve a sequence of these problems. Moreover, in a lot of cases, you might be able to compute this prox operator analytically very quickly so that these iterations can actually be relatively cheap. Before I talk about an example, to get some intuition, I just want to look at, well, what happens if f is actually differentiable? So if f is differentiable, then xk plus 1 is going to be the solution to this optimization problem, and so that means that the gradient of f, evaluated xk plus 1, plus the gradient of this regularizer evaluated xk plus 1, which is going to be 1 over alpha times xk plus 1 minus xk, that expression has to be equal to 0 if xk plus 1 is actually the minimizer. And so if we now just rearrange this and bring xk plus 1 over to one side, what we get is that this is actually an update rule that says let's form xk plus 1 by taking xk minus alpha times the gradient of f evaluated at xk plus 1. And this is almost gradient descent, but notice that what we're actually doing is evaluating the gradient at the place we're stepping to as opposed to the place we're stepping from. And of course, if I actually just wrote down this algorithm and said implement this, you would look at it and say, well, that seems really hard. How will I be able to compute this step direction if the step direction actually depends on where we're going to end up? So it might seem kind of complicated, but the proximal point method is how you would actually do that. Again, I'm just assuming f has a gradient here to kind of illustrate that this is very similar to gradient descent, but we can still use proximal algorithms even when f is not differentiable. You'll see more examples of this in the homework, but first let's look at one concrete and relatively simple example. So suppose we want to solve the standard least squares problem. Now, when A has full column rank, we know the solution to this problem. We have a closed form expression already. It's just going to be A transpose A inverse times A transpose Y. But we've seen that if A transpose A is not very well conditioned, then the inverse actually can be very unstable, and iterative descent methods like gradient descent can actually take many iterations to converge. So what would the proximal point method do here? So the proximal point method would have a core iteration that just looks at solving this regularized least squares problem. This looks almost like Tikhonov regularization. The only difference is that we have the norm squared of x minus xk instead of just the norm squared of x. But using the same approach, we can get a closed form solution for what this is going to look like. It's going to look like xk plus 1 is A transpose A plus delta I inverse times A transpose Y plus delta times xk, where delta here is just 1 over alpha. If you multiply this through, what you can actually show is that this gives you an update rule that says xk plus 1 is xk plus A transpose A plus delta I inverse times A transpose Y minus AXK. Now, when we look at this, each step is equivalent to solving a standard regularized least squares problem. But this problem is actually potentially very well conditioned because we get to choose delta. And as we decrease alpha, or increase delta, then we're adding more regularization. And so even though the number of iterations might increase, what's going to happen is each iteration is going to become very fast because these subproblems are going to start becoming very well conditioned. This is actually a well-known technique in numerical linear algebra called iterative refinement, but it's a special case of the proximal point method, and we'll see more examples of this on the homework. So finally, we haven't talked about convergence yet, and I'm not going to go through the details, but using the same kinds of techniques that we've seen in analyzing gradient descent, you can show that the proximal method will converge to a minimizer of f. In particular, you can show that f of xk minus f star is bounded by the 2 norm squared of x naught minus x star divided by 2 times the sum of the step sizes alpha I up to the kth iteration. So what does this say if alpha k is equal to alpha? So if we just choose a fixed step size, well, in that case, what it tells us is that f of xk minus f star is on the order of 1 over k. And recall, this is much better than the 1 over square root of k, which we had for the subgradient descent method, and it holds for a nice fixed step size of alpha. Now, you might look at this and say, actually, it looks like we can make this converge as fast as we want by making the alpha k to be very large. And this is true. But remember that each one of these subproblems involves solving an optimization problem, and it is often the case that solving those problems depends very critically on what the alpha k are. So as alpha k gets large, we're effectively just solving the original program and not using a proximal method. So one last thing I want to mention about proximal point methods is that we can accelerate it in the exact same way that we accelerated gradient descent, by adding some feedback from previous iterations. So in particular, we can look at an iteration that starts out just like before. So we have x1 as prox alpha f of x naught. But then In the general case, we can take xk to be prox alpha kf of xk minus 1 plus some beta k times a momentum term. This is the same idea as in Nesterov's method, and as before, we can set the beta k in essentially the same way. And if we do so, we can get much faster convergence guarantees. So in particular, if the alpha k, for example, are just chosen to be fixed for a constant step size, we're going to get a convergence rate of 1 over k squared. Now this is way better than 1 over square root of k, and also dramatically better than 1 over k. And moreover, this acceleration really doesn't cost us anything. All we have to do is keep track of one more iterate in memory. So this is really a very cheap and effective way to make the algorithm converge more quickly. Now, there are a lot of other algorithms for non-smooth optimization. So in particular, if we start looking at objective functions f that have some kind of additional structure, like maybe they can be decomposed into a smooth part and a non-smooth part, or can be separated out of the sum of many different terms. And when f has special structure like that, there are often special algorithms that can exploit that structure to get further improvements in performance. But we're not going to spend much more time on this. So starting next time, we're going to move away from solving unconstrained problems, and we're going to start looking at what happens when we add in constraints. And we're going to see how to adapt some of the algorithms we've been talking about to constrained cases.